Hello, so in this video I want to just talk you through the basic underlying principle of what we're doing in this course. Alright, so if you remember that in linear programming we would basically have linear functions. So let's say, for example, we might have f of x equals, I don't know, ax plus b, okay, and we want to minimise or maximise that. Right, and you know, we've dealt with various methods of how we can go about approaching that. Right, but now basically this is no longer a linear function. So we might have, for example, I don't know, x minus 1 times x minus 3, let's say. So basically it might be minimised, something like that. Well, that's clearly, when we expand it out, that's going to be a quadratic, so it's non-linear, right? Because we've got higher power than 1 involved on our right-hand side. We've got squared, we've got power 2, right? So basically the idea is that we want to try and find the minimum of that. Well, can you remember that finding the minimum of a function is a really nice thing to do? It's basically just going to be using calculus. It essentially comes out as a stationary point, yeah? But just in case you can't, so let's say, for example, we end up with something like this, okay, so, you know, a nice curve like that. Okay, basically, you know, if we find the gradient of that, so find out what the gradient is doing. Remember, the gradient is just what the tangent line is doing. So you can hopefully see the tangent line. It's kind of like, a tangent line is just, I think of it as a roller coaster. Okay, you travel along this curve, you know, this is like a roller coaster, and your tangent line is the line of sight. So if you keep your head absolutely still and stare directly ahead as you go along the roller coaster, your tangent line is what you see directly ahead. It's effectively your line of sight. Okay, so that's what the tangent line is doing over here. So over here, hopefully you can see that the tangent line is negative. The tangent line is negative over on the left-hand side. Okay, but then as we go over on the right-hand side, it's positive. As we go over on the right-hand side, it's positive. So basically, what we're doing is we're going from negative to positive. But more than that, hopefully you can see that over here, we're starting off with a really steep negative curve. And then over here, you know, we move to the next tangent line, and it's going to be slightly less steep. And if we keep moving along, what you'll end up with is it'll still be negative on the left-hand side. So on the left-hand side, say if we draw a line down the middle, right? On the left-hand side, it will be negative gradient. So it would be a gradient in the negative direction, yeah? But as we move along the curve, so as we move along the curve, right, it's going to become less steep. The tangent line at those points are going to become less steep. And then actually on the right-hand side, we can say the same about the right-hand side. It's going to become more steep. So it's going to be steeper, but this time in the positive direction. All right. So basically, you know, if we're saying on the left-hand side, that the negative gradient is becoming less steep, are you happy that we're saying that effectively it's becoming less negative? All right, because if you think about it, if we try and write this steep gradient as a number, it'll be close to infinity. It might be, say, 2,000, for example. A 2,000 gradient, a gradient of 2,000 is going to be really, really steep compared to a gradient of, say, 3. Right? So in other words, what we're doing is, as we're moving along the curve, we're becoming less negative. Another way of saying that is we're becoming more positive. And actually that's true. As we move along this curve, we're becoming more positive. Okay, so if I try and write this out, so basically let's say, for example, we have gradients that are coming in and we end up negative 3, negative 2, negative 1. Then doing the same on the right hand side, we go 1, 2, 3, and we keep going. Okay, so they're becoming more positive as we move along the curve. So as we move along the curve, it's becoming more positive, and if we move along the curve in this direction, it's becoming more positive again. So as hopefully you can see, that there must be some point where we make that shift from being negative to being positive, okay? Because we're going from negative, so we're getting more positive, so we're getting less negative, negative 3, negative 2, negative 1, and then we go to positive. So therefore, there must be a point in the middle where the gradient is 0, Okay, so there must be a point in the middle where the gradient is 0. And in fact, there is, and the point where the gradient is 0 is at its lowest point. Okay, because if you think about it, at its lowest point, so in other words, a gradient of 0 would just be a flat line. In other words, it's not changing. Why should it be a flat line? Well, I always think of a gradient as almost like its rate of change. So I almost think like a marble. So if I sit a marble on this tangent line here, then fairly obviously it'll fall down. And likewise over here, if I put a marble here, it'll fall down. So therefore, there's a rate of change. You know, it's an actual value associated with the rate of change. The marble will change, so therefore it has a rate of change, and the speed at which it changes will depend on the gradient. Okay, but here, if I put a marble on this flat curve, it's not going to change. It's going to stay exactly where it is. Okay, so the rate of change at that point must be 0. All right, this is just kind of a reminder of A-level stuff, so just to kind of put it in. So in other words, what I'm saying is that if I find the gradient of this function here and set it equal to 0, then that must be the minimum or the maximum point. The same is also true for the maximum. Just by a stationary point, it'd be the most positive, the highest point or the lowest point of a particular curve. Okay, so how do we find the gradient of a function? Well, we just have to differentiate it. So I'm going to actually expand this thing out. We could use the product rule on this actually, but I'm going to expand this thing out. So I'm going to end up with x squared minus 1x minus 3x and minus 4x, okay, plus 3. Okay, and I know that the stationary point is going to occur where the gradient is equal to 0. So in other words, when I differentiate this, so the derivative of this is going to be, well, it's going to be 2x minus 4, okay? Well, when I set it equal to 0, then therefore there must be the gradient. So in other words, the minimum is going to occur at that point. So in other words, I'm going to say, okay, so the minimum will occur at the point 2x minus 4 is equal to 0, so therefore 2x must be equal to 4, so therefore x must be equal to 2. Okay, so the minimum will occur at the point x equals 2. And basically, if you can get that in your head, okay, and that's fairly obvious. But I mean, how do we know? Then you're part way through learning this course. That's essentially a fundamental idea of this course. When we find the minimum or maximum, we're effectively just trying to find the stationary point of our function. Of course, it's non-linear, so you can't use kind of linear methods anymore. But okay, how do we know that that is a minimum? Well, in order to find whether it is a minimum or not, we have to look at the type, the nature of the stationary point. So in other words, what I'm trying to say is that we find the second derivative. Why should we find the second derivative? Well, the second derivative is the gradient of the gradient. So if I draw my thing out again, so if I draw my quadratic function out again, and I've got my gradients on here. Well, okay, basically what I need to do is I need to consider, well, if I start over here, and if I move along this function, okay, if I start here and I move along this function, and consider what the gradient is doing at each point. So the gradient at this point here, this gradient here, okay, is going to be negative, right? It's going to be negative. Okay, and this point here, okay, the gradient is going to be negative, but it's going to be less negative. Okay, so it's the same kind of idea again. We're getting less negative as we move from left to right. So we're getting less negative, okay? So in other words, another way of saying that is that what the gradient is doing each time, the gradient, okay, is getting more positive. It's getting more positive. So therefore, the gradient of the gradient, so what the rate of change of the gradient should be positive. Because we move along here, remember, as we move along here, how is the gradient changing? Well, it's getting more positive, And what is a way of describing change? Differentiating. So we've just found what the gradient is at any point. So in other words, the gradient is going to be given by 2x minus 4. Okay, so we just sub an x value in here, and that's going to give us the gradient. Okay. Well, basically then, if we find the second derivative, then that's going to tell us what the stationary point is doing. Okay, we basically want the second derivative, so the gradient of the gradient, so how the gradient is changing, we want that to be positive. We want the gradient's change to be positive. Okay, because by this kind of logic, as we move from left to right, the gradient should be getting more positive. Okay, so let's find the second derivative of that. Well, it's going to be 2. Okay, well, as you can see, that is positive, so therefore that must correspond to a minimum. And the opposite is also true for a maximum. With a maximum, you'll find that as we move from left to right, the gradient is getting more negative. Okay, so therefore for a maximum, the second derivative should be less than 0. So the second derivative of x is less than 0. That implies that it must be a maximum. Okay. And if the gradient is equal to 0, well, it's not determined at the moment. But in actual fact, it could be a point of inflection. But again, you'll have to kind of find derivatives, and there's kind of techniques to just check that it is definitely a point of inflection. But if the gradient is if the second derivative is equal to 0, okay, it might be a point of inflection. So in other words, what do I mean by point of inflection? Well, I mean that it's going to go something like this. So in other words, you kind of come in. Okay, you come in with a positive gradient, you then level off, and then you carry on being positive. So it never actually goes negative, or it could, of course, be the other way up. The gradient at every single point is negative. Okay. So yeah, and that's basically the fundamental idea that we're going to explore, and we're going to really use these ideas at the core of them. The last thing that I just want to talk about is the difference between local and global maximums or minimums. Okay, so local and global maximums and minimums. Well, it's kind of fairly obvious. What does the word local actually mean? The word local. Okay, if something's local to you, it means it's close to you. Yeah. Whereas if something's global, it means kind of worldwide, right? It's all over. So basically, the idea is that if you have a function like this, okay, if I just look at minimums, okay, it's the same is also true for maximums, but I'm just going to look at minimums, okay? You've got a minimum over here. Okay? And you've also got a minimum here, all right? Now, this is what would be described as a local minimum. It's a local minimum because it's the minimum of values which are close to that. So in that kind of range, I suppose, of that function, so values which are close to that stationary point, okay, that would be described as a local minimum. But it's not a global minimum because it's not the lowest point of the function overall. The lowest point of the function overall is down here because, of course, it's the lowest point of the function overall, so therefore it's a global minimum. Okay, it's all over. Global means all over. Local means just to that point. So this stationary point here, this stationary point over here, is what we describe as a local minimum because it's the minimum of points which are close to that. Okay, it's the minimum of points which are close to that stationary point. But this would be the lowest point of the function overall, so therefore that would be described as a global minimum. Okay, and the same can also be true for maximum. So essentially in this course, okay, these are the kind of ideas that we're going to be exploring. Okay, and we're going to start off, as I say, with the one-dimensional search. Now, the idea of the one-dimensional search is basically just using one variable, because the dimension, of course, is just a movement in one direction, so either left and right, up or down, forwards and backwards. Okay, and we're actually just going to move in one direction first. But if you can get that in your head, then what you're going to find is really easy is moving on to the multi-dimensional case, because you actually use the one-dimensional case to explore the multiple dimensions. Okay, but you may say, well, hang on a minute, there's only so many ways that you can differentiate a function, right? But what's interesting about this course is because sometimes functions are really difficult to work with, and so therefore the derivatives may be really difficult to find. So what we're going to do in this course is actually look at methods or alternative methods of finding that minimum. So looking at alternative methods than just differentiating. So, rather than not just differentiating, we'll look at alternative methods. Sometimes we have to actually just approximate the minimum. Okay, and these are the methods that we're going to be looking at in this course. So when you can't always differentiate.